Welcome to my talk about securing IoT communication, the path from SSL to DTLS and compact TLS. My name is Hannes Schöfenig and happy to speak here at the Riot Summit 2020. I'm sure you've read statements like IP was never designed with security in mind, or HTTP was never designed with IoT use cases in mind. So let us look about what SSL was designed for. The design of SSL dates back to the early 90s. The first version of SSL was not released publicly. Version 2.0 was released in 1995. The Computer History Museum tells us what time this was. The Nokia 8110 was launched at that time, and the B-Box with a Power PC running at 66 or 133 MHz was introduced. Acorn computers made their first ARM v3 based computer. And the internet connection speed was also slow and used dial-up lines. SSL, as many of you know, was introduced to secure the rise of web-based communication. Around that time, the IETF also published HTTP 1.0, which did not contain persistent connections, although many implementations offered this feature nevertheless. Lacking persistent connections, the TCP connection was torn down and reopened with every request. The capabilities of computers and networking infrastructure did not look too different from what we call IoT today. The work on TLS did not stop in the mid-90s and instead carried on till today. The name changed from SSL to TLS, Transport Layer Security, and here's a timeline of the developments. DTLS, a TLS version used to protect datagram transport protocols, was added later. DTLS 1.0 was written as a delta to TLS 1.1, and DTLS 1.2 is a delta to TLS 1.2. There is no DTLS 1.1. Version 1.3 of DTLS is still work in progress in the IETF TLS working group and hence not shown on this timeline. Most security professionals look at the major releases of the specifications but ignore extensions. Many extensions have been published in the IETF TLS working group, and here are the most important extensions from an IoT point of view. TLS initially supported certificate-based authentication. Support for pre-shared secret-based authentication was added in 2005. Needless to say that the BSK-based version on TLS is much better from a performance point of view in every dimension. Ticket-based session resumption without server-side state was added in 2006 and later updated. It became very popular in enterprise networks for network access authentication and also on the web to keep servers free of security state. In 2011, RFC 666 added several IoT security features, namely the maximum fragment length extensions to allow IoT devices to indicate the buffer sizes, which led to reduced buffer utilization. Client certificate URLs, which allowed the client to send a URL to their X509 certificate instead of sending the certificate with every handshake. Trusted CA indication, which allowed the IoT device to indicate what trust anchors it had to trim down the certificate chain that is transmitted over the wire. In 2014, a new certificate type was added to TLS, namely the raw public key. Certificates are very large, and the idea was to reduce the size to a bare minimum, which is the naked key. With false start, an attempt was made to reduce the latency of the TLS exchange. Cached info reduced the amount of data shared between the client and the server, observing that some of the data is static, particularly in an IoT deployment. Finally, the record size limit extension revised the MFL extension to reduce RAM consumption further. Clearly, a lot of effort went into optimizing the TLS protocol to improve its performance in many environments, and this is only a tiny snapshot of the extensions developed over the years. TLS 1.0, 1.1 and 1.2 fixed security problems and added new cryptographic algorithms, but the foundation was unchanged. Because TLS became the go-to communication security protocol, the interest in breaking it increased. Therefore, not all configurations of TLS are secure. This led to the publication of 2 RFCs that provide information about how to properly use TLS 1.2 and DTLS 1.2 in the IoT environment and for the generic internet, particularly the web. Just to make it crystal clear, using TLS 1.2 and DTLS 1.2 with the recommendation described in these RFCs, you will have a rock-solid communication security solution. With all the work on TLS 1.2 and its extensions, a simple question surfaces. Why do we actually need more? With TLS 1.3, performance was improved and better privacy protection was offered. Many core features of TLS were changed, and due to those changes, the research community was heavily involved in the analysis right from the beginning. When we compare the characteristics of TLS 1.2 and TLS 1.3, we can observe the following. TLS 1.3 reduced the number of round trips, as I'll explain later. But it also increased the number of features. It added a new key derivation function, which provides better security properties and made the formal analysis of the protocol easier. It also added post-handshake authentication messages. The message size in general got reduced. The code size was slightly increased. This was due to the new key derivation function. The energy consumption went down, and as I mentioned, the cryptographic operation went up due to this new key hierarchy. The memory utilization, RAM usage, roughly stayed the same. Big thanks to Emmanuel and Gabriel for the help. We've implemented TLS and DTLS 1.3 plus some extension, tested the code against other libraries, used different IoT device hardware, and investigated several areas of interest. For the sake of time, I will focus on a subset of what is shown on this slide. The key feature in TLS 1.3 is certainly an improved round-trip performance, so let's have a look at it. Here you see the full TLS 1.2 handshake. The important aspect here is when protected application data can be transmitted, which happens here after the first round trip, as the red marking indicates. If you are unfamiliar with security protocols like TLS, on the surface they are all pretty simple. You will see a Diffie-Hellman exchange combined with a certificate-based authentication. A mechanism to ensure freshness has to be added to avoid replay attack, and that's pretty much it. The rest creeps into the picture when you want to have algorithms and extension negotiation, key confirmation of the established symmetric key, and various optimizations. Let me explain the handshake in a little bit more detail. With the client hello, the client indicates what type of algorithms and extension it supports. The server returns the server hello and indicates what type of algorithms and extensions it supports and selects. The certificate message indicates what certificate the server provides. And this is an optional message because the server may not use a certificate-based authentication at all. The server key exchange message is a container for different payloads depending on which type of key exchange method is used. In that sense, TLS is more an authentication framework rather than a single protocol. In most cases, if TLS is used to run an authenticated key exchange with ECDHE and ECDSA, then the server key exchange message will include the Diffie-Hellman key pair. The certificate request is an indication for the client to provide its request back to the server. The server hello then concludes the message exchange from the server side. Next, from the client, if asked to provide a certificate, it will do so, and in the client key exchange, it will provide its Diffie-Hellman key pair. The certificate verify is again optional and used only if a certificate is provided, and then it contains the signature computed over a hash of a transcript. The change cipher spec is the first message that indicates that this new cipher suite had been successfully negotiated, and the finished message is the first encrypted payload in the TLS 1.2 handshake. And subsequently, application data can be sent. Likewise, the server also indicates its completion of the exchange with the changed cipher spec, and then provides the finished message. The finished message uses the negotiated key already and thereby provides key confirmation. If we look at the full TLS 1.3 handshake, we can see that the first application data messages are already sent by the server after receiving the first message from the client. This requires restructuring the information elements sent in the messages. You can also see that most of the handshake messages are encrypted if you look carefully. As a difference to the 1.2 exchange, you will notice that the client hello now contains many more extensions, and those extensions are essentially populated with data that was previously in later messages. So for example, the client hello can now contain a key share, which is the Diffie-Hellman key pair. But what is also worthwhile to note is that there is this encrypted extension message, which, as the naming indicates, takes some of the extensions that were previously found in the client hello and the server hello messages and puts them into this new message, which is encrypted. The server hello message is gone, and also the changed cipher spec message is gone as well, at least in the basic exchange, unless we take the backwards compatibility mode into account, which was introduced very late in the DLS specification work in the IETF due to problems with middle boxes that block traffic that doesn't look like DLS 1.2 exchanges. One of the most important features of DLS 1.3 is probably the ability to transmit protected application data with the first message already. You can't do better than this. This is called the zero RDD exchange. With the zero RDD exchange, the client uses pre-shared secrets established in earlier exchanges and then authenticates the client hello message already. This is indicated by the new extensions early data to indicate that it wants to use early data, the parameters for the BSK exchange methods, and there's also information in there that actually computes the MAC over those messages. And then when the early data is finished, a dedicated signal, the end of early data message, needs to be sent as well. What is worthwhile to mention here is that the use of early data, specifically with the transmission of the first message from the client to the server, it requires some awareness of the potential replay vulnerability. So the application data itself has to take care of making sure that data is not replayed, which may be simple in some cases for some applications, while very difficult to accomplish for others. But that's something to keep in mind. The previous slides about the latency improvement raise an important question. What exactly should we optimize for? And it turns out that there are many potential optimization targets, not only latency, but also code size, RAM utilization, CPU performance, power consumption, bandwidth, and cost. The sad thing is there is a trade-off, and you cannot optimize for everything at the same time. For example, if you care about CPU speed most, particularly of asymmetric crypto, then you can use more RAM to store intermediate results for reuse later. Likewise, you can dynamically compute an AES lookup table instead of storing a pre-computed version in Flash. If you optimize a system, look for the main contributor of the performance bottleneck. This slide shows the code colored according to functionality. In orange, you see the libraries needed for the TLS handshake, and in green you see the code related to public key crypto systems. Gray indicates symmetric key crypto. What you can see here is that asymmetric crypto needs a lot of code, much more than the TLS handshake. Selecting an appropriate crypto library is therefore a worthwhile consideration. Too bad that it's not easy to swap crypto libraries in TLS stacks in practice. Sometimes it's more interesting to look at values that surprise you. Here you see RAM utilization of different configurations compared between Mbed TLS and Wolf SSL, two popular open source TLS stacks. The difference between the stack usage of Mbed TLS and Wolf SSL is surprising. Why is there a constant 8K stack usage in Mbed TLS as colored in yellow? It turns out that the reason is pretty simple. A configuration setting that optimized AES for flash usage and stored the previously mentioned lookup tables in RAM. Unfortunately, different stacks have different ways to configure these features, and sometimes these configuration options are not even available. If a developer wants to get the maximum out of an IoT system, he or she needs to understand the details of the implementation or the configuration, not only for TLS, but for all other software running on the IoT device. This is clearly not a simple task. Following the same logic, let us look at energy measurements. Ignore the detailed values and instead focus on the difference between 1.2 and 1.3. Overall, the improvements are pretty good. But what is the value shown in yellow? It turned out that the DTLS 1.2 implementation allowed multiple DTLS records to be packed into a single datagram, which led to a bandwidth reduction. The DTLS 1.3 implementation did not support that feature yet. Small details matter. If we look at the data sent over the wire, we can observe that the biggest contributor to the message size in a TLS exchange is the certificate. There are many contributors to the size, including a certificate chain that needs to be passed around. It shouldn't surprise anyone that many solutions have been proposed, from simple configuration changes all the way to caching certificates and raw public keys. Extensions that we have mentioned earlier already. And this is still an area of ongoing activity with work on compressing certificates. But let us look at the new features introduced in TLS 1.3, and the added privacy protection is most likely the first thing that comes to mind. Here are screenshots of Wireshark traces of TLS 1.2 and 1.3. As mentioned earlier, the TLS 1.3 handshake mostly consists of encrypted messages. Consequently, more keys need to be derived, which leads to more cryptographic operations, although they only use symmetric key cryptography. Padding was introduced to conceal the size of the payloads, which is optional to use, and the use of buffer forward secrecy is required for certificate-based authentication. Various techniques have been introduced to remove linkability between subsequent exchanges. These added privacy mechanisms have triggered lots of discussions, and some groups are quite unhappy about TLS 1.3 because their ability to perform deep packet inspection has been taken away from them. The TLS working group is even working on encryption of the server name indication, or SNI. With the SNI, the client tells the server what host it wants to contact, and this is important information for any firewall and other deep packet inspection system. In the information society we live in, improvement in security protection are often not welcomed by some. We have seen that SSL and subsequently TLS were primarily used with HTTP-based traffic, but we are here to talk about IoT protocols, right? It is difficult to collect deployment data on protocols used with IoT devices. The Eclipse Foundation conducts yearly surveys among their developer community and asks them, among other things, what protocols they use in their IoT environment. Here is the data from the 2019 survey. Note that I caution to overinterpret this survey because of the size of the ball and the way it is advertised. But this is what we have. HTTP and MQTT are very popular in IoT market. Co-op has, according to this survey, a smaller deployment footprint. If we look at the IoT standardization community, we can clearly observe that the community is split between CoAP, MQTT, and HTTP. With all the standardization work happening on these three protocols, they got very similar in the meanwhile. For example, HTTP initially had text-based headers. Now, those are binary. CoAP initially only worked over UDP. Later, TCP with TLS and WebSocket support was added for traversing firewalls in enterprise networks and to take full advantage of load balancers. MQTT was initially focused on a publish-subscribe paradigm. In version 5 of MQTT, the request-response mechanism was added. Relevant to this discussion is that all three protocols use TLS and DTLS to secure their communication. CoAP was initially designed to run over UDP and DTLS. While TCP was added later as mentioned, many deployments only implement the basic functionality. This does, however, have consequences when IoT deployments happen in environments with stateful packet filtering firewalls and NATs. The NAT timeout differs between TCP and UDP traffic, and the short timeouts for UDP require more frequent keep-alive messages to be sent if the IoT device is supposed to be reachable all the time. While this reachability requirement is not necessarily true in all IoT environments, it is still very common. Since the receiver of a protected record layer packet retrieves the security context via 5-tuple, any change in IP address and port number requires a new handshake to be executed. While this new handshake is likely not going to be a full DTLS handshake, it will nevertheless impact performance. This represents a problem for devices that sleep a lot. So what's the solution? The connection ID or CID adds a new field in the record layer that allows lookup of the security context via the CID rather than the 5-tuple. Like any other extension, is optional to use, and it's available for DTLS 1.2 and 1.3, whereby the 1.3 variant offers better privacy properties due to the nature of the 1.3 protocol with the handshake encryption. The DTLS 1.2 variant is close to finalization, and the 1.2 variant is part of the DTLS 1.3 specification itself. The performance improvement for a certain class of devices are dramatic because handshakes are not needed anymore for a very long time. The additional code, which is less than 1 kilobyte on the client side, more than justifies this extension. Let us jump from the standardization world to the implementation of TLS extension. I looked at various embedded TLS and DTLS stacks, and here's what I found out. Upfront, it needs to be said that the development of security software takes a lot of time, and the embedded software market is conservative. Please also keep in mind that the data in the table shows release code rather than prototyping code. TLS 1.3 is available in popular embedded stacks today. The embed TLS code is still at an experimental level. DTLS 1.3 code is, of course, not yet released because the specification hasn't been finalized yet. The CID solution for DTLS 1.3 is currently only implemented in embed TLS because, again, it's not finalized yet. What surprised me the most is that many extensions developed to optimize IoT communication are not implemented. It is difficult to speculate about the reason. Is TLS without extensions already good enough for the IoT deployments? Are companies unaware of those extensions or the value they provide? Or are there other reasons? The last surprising insight is the positive implementation status of raw public keys. It would be interesting to know how the deployment status looks like. From the Excel data on the last slide, one might not be convinced in the need for further optimization of TLS. This has, however, not discouraged the standardization community from starting 2 new standardization journeys: Lake, the lightweight authenticated key exchange, and cTLS, compact TLS. I will focus on cTLS due to time reasons. cTLS compresses the handshake of TLS and DTLS while maintaining the security properties of TLS. Compression is a technique that is frequently applied in the IoT context. Look, for example, at all the IPv6 header compression work done with 6LoWPAN and the following 6Low group. With cTLS, integers are encoded more efficiently, fields only needed for backwards compatibility are removed, and a new certificate compression scheme is introduced. Probably most interestingly is the ability to extend the cipher suite concept to extensions and parameters in form of profiles. Instead of performing an a la carte negotiation, profiles with common settings are used instead. On the left, you can see the result of this compression with the full TLS 1.3 ECDHE ECDSA handshake cut down to a little more than 300 bytes. Note that this work is in early stages, so it's a good time to provide input or to help out with research. I would like to reuse a slide from Henning Schulzrinne, who published an article with his reflections on networking research. I believe those statements offer food for thought. He shares his thoughts about networking research and says, most engineering is cost optimization, but it is hard because the cost data is not available. Improvements are in operations and management more than in protocols and algorithms. Better software skills are required. At least the last part is something that is certainly present in the Riot community, but the first two bullets are certainly something to think about. And with this, I would like to conclude. And if there are any questions, please don't hesitate to ask now or later in the hallway. Thank you.